All right, students, let's work some more problems. I was just looking over some, and I want to work 3 more for Chapter 11. So let me make sure my pen is ready to go. So this is Chapter 11, page 357, if I'm not mistaken. Okay. Number 17. Okay, so we're going to look at number 17. Be looking at part A to start with. It says the boom shown in figure 11.17. So let's go ahead and draw it. We have a boom, and I'm not going to draw all the fancy stuff. There's a 60-degree angle. It has a mass hanging from it. Okay. The boom weighs 2,600 newtons. So the weight of the boom is 2,600 newtons. And is attached to a frictionless pivot, so it is frictionless. At the lower end, which is talking about down here, okay? It is not uniform. All right, let me make sure my glasses are focused right here now. It is not uniform. The distance of its center of gravity from the pivot is 35% of its length, okay? So it's 35. So in other words, let me read that again. It says the distance of its center of gravity from pivot is 35% of its length. So the center of gravity is 0.35 times L, okay? All right, so CG is converted to a decimal, all right? Find the tension in the guy wire. Okay, so we got to find the tension in the guy wire. So where's the guy wire? Well, there's a tower that comes up and comes over here. So this is the guy wire. So we want to find the tension here. So the tension in the guy wire. Okay? All right. And by the way, notice that the weight of this is 5,000 newtons. Okay, so we have the weight pulling down, and of course we have the tension in the guy wire, tension in G, okay? And then we have the 60-degree angle with the boom with the ground, okay? So what kind of problem is this? Well, first of all, we need to look at two quantities or two particular phenomena that are at work here. One being force, one being torque. Remember, this chapter deals with equilibrium. So what we have to do is determine, are we at equilibrium? Is anything rotating? Is anything accelerating? Okay. So how do we write that? Well, we have to write it this way and say that the sum of all the torques, well, nothing is rotating. Okay. So therefore, there's the sum of all external torques is equal to 0. And nothing is accelerating, so the sum of all external forces is equal to 0, okay? So that helps us out a whole lot, all right? That helps us out a tremendous amount, okay? So what do we need to do now? Well, we need to find the tension in the guy wire. Well, how in the world do we find the tension in the guy wire? All right, well, guys, you got to remember your geometry, okay? If this angle is 60 degrees, then guess what? This angle right here is 60 degrees, okay? Opposite, what is that theorem? Opposite adjacent. I never can exact. I just know that the opposite angles there are congruent. Opposite adjacent, is that right? Okay. I remember the theory. Opposite angles are congruent there, okay? All right. Well, that's very important, isn't it? Now, we want to find the tension, which is here. Well, now, look, y'all, here's your hypotenuse. And by the way, did it give us a length of hypotenuse? No. Did it tell us the length? No. But it does tell us it's 35% of its length. The boom is, okay? All right. So we have, what all forces do we have at work here? Well, we've got we got the weight of the load, okay? We've got the tension in the wire, guy wire, and we also have the weight of the boom, don't we? Okay. Well, sure we do. Okay. So remember, we're going to work this from a torque standpoint because we have a distance and we have a force, a tension. So let's solve it that way. So we've got the tension in the guy wire times the length. Now, what equation are we going to use? Okay. Well, are we going to use sine or are we going to use cosine? Well, for the actual guy wire, we're going to use sine because it's what? Well, it's the opposite over the hypotenuse, right? Because look, guys, this wire and that wire are basically the same, okay? Just because there's a pulley there doesn't change anything. Let me make sure on that now. Okay. All right. So we're going to use sine, and so we got TL times sine of 60 degrees. Okay. Because remember, it's torque now. And then we're going to look at what? Well, now we're going to look at the weight of the load and the weight of the boom. And let me make sure I've read this right. That it's not, the distance of its center of gravity from the pivot is 35% of its length. Yeah, talking about the boom, okay? All right, so we've got the tension times the length, sine of 60. 1 second. Okay, sorry about that. Minus, now look, we've got the weight of the load and we've got the weight of the boom. The weight of the boom is going to be down, and the weight of the load is going to be down. Now remember, it said that its center of gravity is not exactly in the middle. It's 0.35% of, or excuse me, 0.35 or 35% of the length. Now I didn't put that at 35. Let me go back and fix that. I'm just going to kind of guess it here. Well, this would be half. So we're going to say somewhere right in there, okay? Just approximate. So we got the weight of the load times what? L cosine of 60. Now, why did we use cosine? Well, again, it's the adjacent over the hypotenuse, okay? Adjacent over the hypotenuse. Adjacent over the hypotenuse. See, weight of the load. See, you got the guy wire, then you got the weight of the load. If you look at your geometry, adjacent over hypotenuse, adjacent over hypotenuse. Okay, now, minus, I wished I'd have written it all down here, the weight of the boom times 0.35 L cosine of 60 degrees, of course. All right, is equal to 0. All right. All right. So now you should have all your math done now, okay? Or the physics done. So now let's solve for T of the guy wire. And then that, of course, becomes what? Well, that becomes this right here. I guess I can go ahead and write it out. Let me just go ahead and start filling everything in because I want to get this all in on one slide. So you solve for this right here, and your equation becomes what? Well, that means you got to add those to the other side. And so it becomes what? it becomes 5,000 newtons, because it's the load. 5,000 newtons cosine of 60 plus the weight of the load, excuse me, not the weight of the load, the weight of the boom, which is 2,600 newtons, times what? 0.35 of cosine of 60. Okay, and you say, well, where's your L here? All right, we're letting L be 1, okay, because notice it didn't give us a length. So we'll just say, since we know that the center of gravity of the boom is 35% or 0.35 of L, then L is assumed to be 1, okay? That's why there's not an L here, okay? We're just, again, we're assuming it, okay? That it's 1, since they didn't give us a length, but they did tell us that the center of gravity was 0.35 or 35%. So I don't want you to think I'm leaving something out, because I'm not, okay? You got to think about your mathematics. And then we're going to divide by L sine of 60, and L is 1, so it's going to be what? Sine of 60. Okay. And what do we get? We get a tension of 34.12.1 newtons, or you can write it this way, 3.412 or 41 times 10 to the third newtons. Okay, so there is our, there is part A. Okay, so that's the tension in the guy wire. I should have wrote the G there, okay. And it did say find the tension in the guy wire, yeah. Now it says the horizontal and vertical components of the force exerted on the boom at its lower end. Start with a free body diagram, okay. Well, we've actually already drawn everything. You had the weight of the load, you have the tension going back in this direction, then you had the weight right here. It's a little hard to see. Let me erase. And I always like to try to start out with the free body diagrams, because I tell you, if you'll do that, y'all, it'll make it a lot easier. So here's the weight of the boom right here, and of course this was 60 degrees, that right there was, okay, the weight of the boom. So we actually already have all of our free body diagrams, okay, and of course you can draw a force up here, because you do have a force going in this direction, okay, because of the guy wire, okay. All right, now, so we know then that the sum of all the forces is equal to 0. It's not accelerating. So we have determined the tension in the guy wire, okay. So we have, let's back up. So we have the tension in the wire right here, which is a force. We've already found it. Minus the tension in the what? Minus the tension in the boom, right? So what does our equation look like? Well, and we are looking for what? We are looking for, let me make sure I've got this right now. We are looking for, we're wanting to know the vertical components of the forces exerted on the boom at its lower end, which is down here. So we're looking for the vertical forces, okay? The vertical forces. So what does that look like? Well, okay, we found the horizontal force, didn't we? Yeah, that's right here. T of G is also the horizontal force. So you got a horizontal force going that way, and you got a vertical force going up, right? So what does that equation look like? Well, come on, guys. That's going to be F of H minus what? Tension of G of the guy wire is equal to what? 0, because it's not accelerating. So now we have what? Well, we've got so those basically are 0. They cancel each other out. They have to, y'all. You say, well, how do you know that? Well, come on, guys, look. Look. It's not accelerating, okay? So if you have what was it? 3.41 times 10 to the third Newton force in this direction, then you've also got to have the same force, in the horizontal direction as you do in the vertical, okay? So in other words, they're canceling out. So now we can find the vertical force, okay? The vertical force, okay? Vertical force upward. So we have what? Well, we write our equation like this. We say the vertical force minus the weight of the boom minus the weight of the load is equal to 0. So then the vertical force is equal to what? The weight of the boom plus the weight of the load. Well, put them together, y'all. The vertical force is equal to what? We've got, the weight of the boom was 2,600 newtons, and the weight of the load was 5,000 newtons. So the vertical force is what? 7,600 newtons, okay? It has to be. Because remember now, it's talking about at the lower end, okay? At the lower end, okay? Okay, I hope that helps on that problem. And that was what, part B? Yeah, that was 17B. All right. Okay. Now let's look at question, we're still in chapter 11. Oh, was it question 27 I wanted to do? I think it was. So let's look at question 27, which is on page 359. So we got chapter 11, and we got question 27 on page, what I say, 359? Yeah. Okay. We got a circular wheel, we got a circular steel wire, 2 meters long, must stretch no more than 0.25 centimeters when a tensile force of 7,000 newtons is applied to each end of the wire. Okay, so we've got a wire. Now, it said a round wire, so let me see if I can draw this properly. I'll do the best I can. I'm not an artist by any stretch of the imagination. So we got it's round on that end, and then we come down here, and does that look right? Okay, close enough. All right, so it's a circular wire, and the length of the wire is 2 meters long, and it can stretch no more than 0.25 centimeters. So its stretch is 0.25 centimeters, or, wow, that would be 0.0025 meters, right? Or 2.5 times 10 to the negative third meters, right? Yeah, move your decimal place. And that's what? What is that value? Well, that's delta L. That's actually delta L. Okay, that's the change in length. That's the change in length. All right? And so the tensile force, That's applied to each end. And by the way, how do I write that? Well, you can write it like this. You can say F perpendicular is what? 700 newtons to each end, okay? All right. So we've got to do what? We've got to find the what? It says what minimum diameter is required for the wire. So we want to know the diameter minimum. Question mark. Well, how in the world are we going to find that? Well, y'all, we're going to use Young's modulus. So we know that Young's modulus, because this deals with tension, is equal to, it's not bulk and it's not shear. It's a Young's modulus. It's a tensile strength. Okay, it's tensile. It's not bulk and it's not shear. We're looking at tensile, and we know that Young's modulus is what? Well, it is the initial L times the tensile force, or the force applied to each end, divided by what? The area of the wire times what? The change in length. Now we can write it this way, delta L. Okay? So how do I find diameter? Well, when we look at area, how do we find the area? And by the way, and by the way, we're looking at cross-sectional area. Cross-sectional area. And how do we find area? Well, cross-sectional area is real easy. It's pi r squared, isn't it? It's pi r squared, okay? So look, we can find diameter from radius, right? We can find the radius, which is equal to what? Well, it's equal to what? The square root of the area divided by pi, all under the radical. Is that right? Yeah. Yeah, we can find the radius by doing it that way. So let's do that. So let's solve for A, solve for area, and it becomes what? The initial length, tensile force, times divided by what? Young's modulus, times the change in L, the change in length. Now, it tells us that it is a what? It's a steel wire. So I've got to know the Young's modulus. So what is the Young's modulus for a steel wire? Well, I go to my chart and I look it up. I go to page 347 and it tells us that steel okay. I want to make sure I'm looking at this right now. Yeah, there it is. Steel, and I wish they wouldn't write it this way, is 20 times 10 to the 10th. I don't like to write it that way, y'all. I don't know why. And that's PA. This is how I'm going to write it. 2.0 times 10 to the what? The 11th, PA. And PA is what? PA is newtons per meter squared. You better not forget that. You say, why do you want to write that? Because I've got one significant figure to the left of my decimal, and I don't have two. Okay, I don't like writing it that way. I'm going to say 2 times 10 to the 11th, PA. All right, but you can write it that way. I don't care, okay? I mean, to me, I've always been taught that you only have one whole number to the right of the decimal when you write scientific notation. That's the way I was always taught, that you really don't need no more than one to the left, okay? And then you need to use your SI prefixes, if at all possible, okay? So we could actually write that as what? We could write that as 2, let's see, you're going bigger. We could write that as what? 200? Yeah. Giga. We could use giga in there, couldn't we? Okay. Well, we'll leave the power there alone, okay? All right. Or am I doing that backwards? It would be, if it's times 10 to the 10th PA, I'm actually going, yeah, 200, yeah, because giga is under, yeah, that's right. So it'd be 200 gigapascals. Yeah, okay. You can write it that way, because giga is smaller than the 10th. All right. Okay? So let's plug everything in now, find the area. I like to try to go over these units with you. All right, so the initial length was 2 meters, right? So it's 2 meters times the force, which was what, 700 newtons, divided by 2.0 times 10 to the 11th. And I'm going to go ahead and write it this way, newtons per meter squared. I hope nobody flips out on me. And then I'm going to put in my change in length, which is 2.5 times 10 to the negative third meters. Or we could say 2.5 millimeters. We could say 2.5 millimeters. We could use our SI prefix there, y'all, because 10 to the negative third is milli. So we could say that. Okay? And so we get an area of what? Well, let's see. Our area is 2.8 times 10 to the negative 6 meters squared. So it's 2.8 times 10 to the negative 6th. We could call that micro. All right, we could say 2.8 times 10 to the negative 6 micrometers squared. Now, I'm telling you guys, 2.8 micrometers squared, not times 10 to the negative 6, because micro is 10 to the negative 6. Your engineering professors are going to want you to use these prefixes. So we could say 2.8 micrometers squared. Okay? All right? So you need to be learning them. Now, how did we get to that? Well, let's see. These meters cancel out, the newtons cancel out, and we're left with meters squared. Okay? That's how we get to that. Now we know the area, we can find the radius. So the radius is equal to what? Well, we've already determined that it is the square root of the area divided by pi. All right, so we just put it under the radical, and so we say 2.8 times 10 to the negative 6 meters squared, all under the radical, divided by, and by the way, you use pi. You better not put in 3.14. Y'all, that is 5th and 6th grade arithmetic, okay? All right? You do not do that. If it says pi, you use the pi button on your calculator, okay? Do not put in 3.14. All right, so the radius comes out to be what? The radius is 9.4, so it comes out to be 9.4 times 10 to the negative 4th meters, because you remember now you take the square root of a square and it becomes meters on the meter square. All right, 9.4 times 10 to the negative 4th meters. And so how do I find the diameter? Well, we say times 2. And so the diameter then comes out to be 1.89. 1.89 times 10 to the negative third meters, or we could say 1.89 millimeters. Okay? All right, there's your answer. There's your diameter, 1.89 millimeters. Or let me go ahead and write it, 1.89 millimeters. Okay? All right, that's not much, is it? But y'all, it is what it is. Now remember, when you're dealing with tensile and bulk and shear, you know, sometimes you may be dealing with just some very, very small changes. Okay, but those can be enormous in the realm of the integrity of the structure. Okay, you know, just subtle changes in the length of a bridge can have enormous impacts on the integrity of the bridge. So you have to remember that. Okay, now let's look at one more in chapter 11. And we're going to do a bulk's modulus problem, number 35. So this is number 35. It's chapter 11. And we're on page, I think the same page, 359. Okay. All right, so we have a specimen of oil having an initial volume of 600 centimeters cubed, is subjected to a pressure increase of 3.6 times 10 to the 6th PA, and the volume is found to decrease by 0.45 centimeters cubed. what is the bulk modulus of the material and what is the compressibility of the material. Okay, so let's write down what we know. We know what? We got a drop of oil, and the drop of oil is, let's see, it is subjected to a pressure. So we got a pressure applied. All right, that's pressure, small p, okay, on the drop of oil. That's small p. And let's see, what was the volume? So the initial volume of the oil is what? 600 centimeters cubed. Now, guys, you know what we're going to have to do. You know we're going to have to convert that to meters cubed. How in the world do we do that? Well, it's going to come out to be, and I'll show you in just a second, 6 times 10 to the negative 4th meters cubed. How did you come to that, Mr. Shields? All right, guys, watch. All right, if we draw our box, okay, and I taught this in class at the beginning of the semester. Okay, 1 meter is how many centimeters? It's 100. 1 meter is 100. 1 meter is 100. Okay, so 1 meter cubed is equal to what? Well, 100 times 100 times 100 is what? 1,000,000. So that's 1 times 10 to the 6th meters cubed. Is that right? 246? Yeah. Yeah. Okay. And then when you take, look, when you take 600 centimeters cubed, and wait a minute, that's centimeters cubed, so 1 meter cubed. So when you take 1 times 10 to the 6th centimeters cubed, my bad, and 1 meter cubed, those cancel out, and you got 600 divided by 1 times 10 to the 6th, and what do you get, folks? Well, you should get 6 times 10 to the negative 4th, which is exactly right. But I showed you how to do that, okay? All right, so that's the initial volume, and then it has a delta of what? It has a delta, and that's a lowercase p, of positive 3.6, and that's real important you write that, times 10 to the 6th PA. Now, of course, that's newtons per meter squared. Okay. All right. Newtons per meter squared. And the volume is found to decrease by 0.45 centimeters cubed. So how do we write that? Well, we have a change in volume of negative 0.45 centimeters cubed, which is going to be what? Well, you convert that to meters, and it comes out to be what? A negative 4.7. Ah, shoot, not 4.7, 4.5. I don't know where I got the 7. 4.5 times 10 to the negative 7th meters cubed. And y'all, you have to convert it. You have to convert it. Okay, 4.5 times 10 to the negative 7th meters cubed. Or you could say 0.45 micrometers cubed. You could move the decimal one place to the left and say 0.45 micrometers cubed. Okay? And notice I had to put that negative on there, and why did I do that? Well, y'all, because it tells us it decreased. Okay? It tells us there was a decrease. So you have to put the negative because the volume decreased. Just like you had to show that the pressure was positive. Now, remember I talked about this in the lecture video, and I did a virtual lecture yesterday, and I really drove this home, or I hope to God I did. And so we're looking for bulk modulus, aren't we? Well, how do we find the bulk modulus? Well, bulk modulus, by definition, is equal to what? It's the negative change in pressure times the initial volume divided by the change in volume. Okay? And don't forget the negative. Now you say, now where did you get that from? Well, I got it from this right here. I got it from delta V over initial V is equal to negative delta P over Bulk's modulus. And so you solve for Bulk's modulus. So here's the equation. All right, so let's plug everything in. So Bulk modulus is equal to, well, it's the negative now. What was the change in pressure? Well, it was a positive change in pressure, 3.6 times 10 to the 6th. All right, and we're just going to leave that PA, okay, times the initial volume. Remember, it's got to be in meters now, which is 6 times 10 to the negative 4th meters cubed, or we could say 600 micrometers cubed. We could use our prefixes, guys. You need to be learning to do that. All right, and then divided by the change in volume. Oh, I love it when the math works out, which is a negative 4.5 times 10 to the negative 7th meters cubed. Or we could say 0.45. I thought you said a minute ago, Mr. Shields, you wanted 1 when you did scientific notation. Yes, except when you're using the prefixes, okay? And when you're using the prefixes, then you throw that rule out the window. So you would say 0.45 micrometers cubed if you wanted to put that in the SI prefix, okay? So yeah, I should have gone ahead and told you that, but yeah, you throw the rule out if you're using the SI prefixes of the one whole number to the left of the decimal. You don't have to have it there, okay? All right. And so we do all the crazy, wild arithmetic. Notice how the negatives cancel out. Notice they cancel out. Notice the meters cubed cancel out. Notice that's why I left it in PA, because bulk modulus has to be PA. And so what do we get? We get a 4.8 times 10 to the 9th PA. 4.8 times 10 to the 9th pascals, okay? And of course it is positive because the negatives cancel out, okay? All right, now how do we do, y'all, how on God's earth do we do compressibility? Well, okay, y'all, it's the reciprocal of that. And so compressibility K is equal to 1 over the bulk modulus. Well, that's hard, isn't it? So we got 1 over 4.8 times 10 to the 9th PA. And so the K value, the compressibility value, is 2.08 times 10 to the what? Negative 10th. Now watch this. Reciprocal PAs. Say, huh? 2.08 times 10 to the negative 10th. Reciprocal PAs. And again, you could use an SI prefix. Oh, shoot. And what is the SI prefix for 10 to the negative 9? Nano. Yeah, crazy head. I can't believe I went blank there for a minute. So if I wanted to convert that to nano reciprocal pascals, I would move my decimal one place to the left and say 0.208 nano reciprocal pascals. And you say, what? How in the world? Come on, guys, look. Negative 1 means 1 over PA, okay? See, look right here where your PA is. So yeah, we just write it negative 1. We just say to the negative 1 or reciprocal pascals, because that's what compressibility is. It's the reciprocal of Bulk's modulus, okay? So don't flip out on all these numbers on me now. You just got to remember, you got to think, you got to remember the concept we're talking about. Compressibility is reciprocal of bulk, okay? Okay. All right, and that was number 35. So I hope this has helped.